Hello, everyone. Thank you very much for organizing for invitation me. And today I shall speak about uh, um, anything which concerning the bicyclic monoid. So we should start. Okay. So, what is a bicyclic semigroup? Bicyclic semigroup or bicyclic monoid is a semigroup with the identity which is generated by two elements P and Q, subject only to condition P multiply Q is equal to 1 identity. Yeah. So, the semigroup operation of the bicyclic monoid determined by the following formula. Also, if we consider square of omega, with the following semigroup operation. This semigroup is isomorphic to the bicycle monoid by the following mapping: Q in power K P power L maps to KL. So also the set BZ, which is equal square of the integers, with the semigroup operation defined by the formula 1 is called the extended bicyclic semigroup. What is property of such semigroup? Very nice property that all no-identity homomorphism of the bicyclic semigroup and the extended bicyclic semigroup are group. Also, there are many results about this semigroup, or for example, on topologization, any Hausdorff shift continuous topology on the bicyclic semigroup or on the standard bicyclic semigroup is discrete. Also, any non-isomorphic homomorphic image of the bicyclic semigroup or the extended bicyclic semigroup is a cyclic group. So first question, what are endomorphism of the bicyclic semigroup and the extended bicyclic semigroup? So not very old theorem, any endomorphism of the bicyclic semigroup has the following form. Also similar we get for the extended bicyclic semigroup. And the semigroup of endomorphism of the bicyclic semigroup is isomorphic to the semi-direct product omega with the usual addition to with omega with the usual multiplication. Similar, we get that the semigroup of all endomorphism of the extended bicyclic semigroup is isomorphic of the semi-direct product additive group of integer and omega with usual multiplication. So what will be if we consider some extension or some subsemigroup about some semigroup property of endomorphism will be a report of Shirley-Penza today, but I give some property of some extension of the bicyclic extension of some groups or simply bicyclic extension. So if we have partial ordered group, yeah, we may to consider what is special order group. So group with special order such with preserve this group operation preserve order is called special order semigroup. If this special order is a total order or so-called linear order, we shall call this semigroup totally ordered. And if the last inequality holds, yeah, for if for any element of group there exists a positive integer such that some element in large power is greater or equal previous element, such group is called a Hermitian. So if we consider homomorphism of a linearly ordered semigroup, we can consider such homomorphism which preserve a partial order, and such homomorphism we shall call O homomorphism, or if this homomorphism will be isomorphism, we shall call it O isomorphism. And similar endomorphism, O endomorphism, and similar O automorphism. If G is a totally ordered groups, on the product of positive corner on its square, positive corner, we define the following operation. If we left to the additive group of integer with usual order, such operation gives operation of the bicyclic semigroup, where multiplication is usual addition, and power is multiplication on the power, yeah? So such semigroup is called the bicyclic extension of the totally ordered group G. What are properties of semigroup? If G and H are Archimedean totally ordered groups, then every homomorphism from G to H generate a monoid homomorphism from the bicyclic extensions, and every monoid homomorphism which preserve order, yeah, which generates a homomorphism by the following formula. And we get the following very nice theorem. Let G be a Archimedean totally ordered groups, then a semigroup of O endomorphism of G is isomorphic to the semigroup of endomorphism of monoid, which is a bicyclic extension of the group G. And in this case, we have a similar for a group of automorphism of extension and a group of automorphism, ordered automorphism of G. Yeah. So if we consider such category where objects are first category objects are Archimedean totally ordered groups, and morphism are homomorphism of Archimedean totally ordered groups, and category of bicyclic extension of such groups where objects are bicyclic extension of such, and morphism are homomorphism of monoids. We get that these two categories are isomorphic. So first of all, I don't know what will be in general case, for example, non-Archimedean groups, ordered groups. I don't know what will be also a case when we have not total order, we have a partial order on a group. I don't know answer on this topic. So the next extension, which was presented by me and my student Mykola Michelenic. If P omega is a family of this all subset of omega, for any element of P omega and any non-negative integer n and m, we define such set m minus n plus f. Yeah, even say that the subfamily f of P omega is omega closed if the following condition holds, like for any n and f1, f2 from family f. And on the product B omega with this family f, we define the binary operation in the following way. If we consider this operation and we cancel the set coordinate, this semigroup will be isomorphic to the bicyclic semigroup. And very, very simple, not very simple complication. Also, this set is a semigroup, and if we consider the risk if I is ideal, what is ideal? Where is a subset of this product, I, E, and empty set, yeah? So it's triple form an ideal. We consider risk coefficient semigroup by this ideal. We obtain B omega F semigroup. Such semigroup has many perfect property. Such property I find here. It's not interesting, but in some case, this semigroup is isomorphic to the bicyclic semigroup. What is this case? The semigroup B omega F is isomorphic to the bicyclic semigroup if and only if the family F consists of one set with is non-empty and is inductive. What is inductive set? Set F is called inductive if X belongs to F implies X plus 1 belongs to F. Because that omega is inductive subset of P omega, yeah? And corollary very simple. The semigroup B omega F contains a isomorphic copy of bicyclic semigroup if and only if the family F has a non-empty inductive subset of in omega. So, first question: if we consider the family F, which consists of inductive subset, what is the property of big omega F? What are endomorphisms of such a semigroup? So if we consider this theorem, so we get some property which shows that such extension is very close to the bicyclic semigroup, yeah? The following three conditions are equivalent. B omega F is B simple semigroup, equivalent to the condition the family F contains exactly one element, and B omega F is either trivial or isomorphic to the bicyclic semigroup. Also, what will be when the family F consists of two elements? One set is non-empty and contains one element, and the second set is empty set, yeah? Then this semigroup will be isomorphic to the semigroup of matrix Unix, countably semigroup of matrix, and the following statements hold. When is such extension is zero B simple, this equivalence the following: this B omega F is isomorphic to the holds only three cases. There are no other cases that either B omega F is isomorphic to the semigroup of omega matrix units. B omega F is isomorphic to the bicyclic monoid with adjoint zero, and the family F consists of the following family: empty set and G multiply omega for some G greater or equal to. Що ви так повільно? What will be so every inverse semigroup admits minimal group congruence, which is defined on the following formula, yeah, and we have the nice proposition that if F is a family of omega closed subfamily of non-empty inductive subset of P omega and empty set does not belong to F, then two elements are in sigma equivalent or I equivalent on a minimum group congruence in and only if the following condition holds here. And this implies that the quotient semigroup B omega F by minimal group congruence is isomorphic to additive group of integer. So similar we have for the bicyclic semigroup and for the extended bicyclic semigroup. If we consider the bicyclic semigroup, well know that every optomorphism of the bicyclic semigroup is trivial. It's a identity map. But when endomorphism of the bicyclic semigroup is identity map, if and only if it has two distinct fixed points. So in our case, when we have a family of non-empty inductive subset of omega, yeah, so the following three conditions are equivalent. Endomorphism E is identity self-map of B omega F. Endomorphism E has three distinct fixed points, and endomorphism C has a fixed point which is not an idempotent of B omega F. So later by that notion, we denote such array is start with A, yeah, in omega, and we denote F2. The family which consists of two subset array 0 of 0 array and 1, yeah, and we start to establish endomorphism of the semigroup B omega F. So we proved that there are two such endomorphism by two formula, yeah, alpha and the second beta. So these two types of endomorphism are injective endomorphism. And first question is there other injective endomorphism? Me and Inna Pozniakova, we proved the following small theorem. This theorem states there are no other injective endomorphism of the extension B omega F when F consists of injective, where F consists of two inductive sets, array 0 and array 1, yeah, and all property of multiplication are demonstrated in this file. Also, we describe all non-injective endomorphism of such extension, but it's very, very large description, and it was published in two papers, large papers, at least 15 or 25 pages, yeah. And what will be when our family is more large, which contains three elements, yeah? This problem we solve with Marko Serivka. And we show that only such endomorphism of B omega F, there are no other. So if epsilon is an injective endomorphism of the semigroup B omega F, yeah, where F consists three inductive subsets, that epsilon is equal alpha k for some positive integer k. There are no other. Very, very, not very simple, but for my opinion, simple proposition that monoid of injective endomorphism of B omega F, where F consists of three elements, is isomorphic to the set of positive integer with usual multiplication. What will be when the family F consists 4 and more? We don't know, but we have such a hypothesis that all injective endomorphism of such extension are automorphism, and hence are trivially equalist identity map. We consider two cases. We have F consists of one singleton set and empty set, yes, and inductive subset. Or what will be when our family F consists of finite subset of omega, yeah? When we can fix any positive integer n and consider such finite interval of omega, and we get the following statements. This result is common with Oleg Gutik, that this semigroup is isomorphic to inverse subsemigroup of the bounded finite partial transformation of omega, and it is isomorphic to the partial convex order isomorphism of omega with a rank equal or less n. Also, very nice statements for these semigroups that all congruents on such semigroups are real. What does this mean? Such congruence is generated by ideals, by two-side ideal. And also we prove the following theorem that every homomorphism of such semigroup is either isomorphic to this semigroup or is a singleton semigroup or is a trivial semigroup. This also this result also are published with Oleg Gutik. And the next state shows that the semigroup or rejected endomorphism of such semigroup or isomorphic semigroup is isomorphic to omega with usual addition, yeah, and hence we get the group of automorphism of such semigroup is trivial. Also, only Gutik describe all non-injective endomorphism of such semigroup, but in this case, but in this very difficult description, and I left it. Oh, sorry. What about topologization? So I start with the following statement that every Hausdorff shift continuous. What is shift continuous topology? That left and the right translation of the semigroup are continuous map. All if we consider b omega when f is any family of non-empty inductive subset of omega, then every shift continuous Hausdorff topology is discrete. So in terminology of topological algebra, this means that such semigroup is not topologized as semi-topological or topological semigroup. When the set is finite, there are many different topology, but this topology is the following: that all elements is distinct with zero, yeah, are isolated, but at zero may be very distinct base. For example, if we have a compact topology, topology such as this topology, that means the structure of semi-topological semigroup, this equivalence that this topology is pseudo-compact or countably compact, also, or edge-closed as a topological space. So also similar result was published by Inna Poznikova and me when we consider omega closed subset, not omega or in the set of integer. And Inna today plan to discuss on this topic. Also, Marcos Rivka make a report about what are non-monoid endomorphism of the B omega F when the set of the family F consists of two inductive subset, not empty inductive subset. No, that is all. Thank you for your attention.